Is the number of objects here even or odd? Well, you can tell immediately because objects pair up nicely and one object remains. However, if you were asked to test whether the number of objects is divisible by 3, that seems to be quite a bit more challenging. And if objects are given like this, there does not seem to be a way that's better than counting all of them. In our paper, we count objects, modulo some number m. The objects we count are subgraphs, namely specific kinds of subgraphs in a large given graph. Matchings, matching-splittable graphs, and paths. We have both upper bounds, which means algorithms, and lower bounds, which means hardness results, both in the parameterized complexity sense as well as in the exponential time complexity sense. So we have lower bounds under assumptions from parameterized complexity and under the exponential time hypothesis as well. So the topic is modular counting of subgraphs, and we start with paths. Here is a given graph with two vertices S and T. How many paths from S to T are there that have 3 edges? Well, it turns out there are 3 such paths. The exact counting problem is given some host graph H and a number K as input. And it is then asked to count the number of paths that have exactly K edges. Let's say this number is 140, just as an example. 140 can be represented in 8 bits like this. And the exact counting problem is to compute all of these bits. So what's the complexity of this problem? Well, this is, of course, being a generalization of the Hamiltonian path problem, number p hard, which means it cannot be computed in polynomial time unless the polynomial time hierarchy collapses. The problem is also, when we parameterize it by k, number w1 hard, which means there cannot be a fixed parameter tractable algorithm for it unless fpt is equal to w1. There are, of course, variants of this problem. The more classical problem is the decision problem, where we just want to know whether the number of paths that have k edges is at least 1. So the answer in our example would be yes. And we get yes from the bit representation just by taking the OR of all bits. We just want to know whether at least one of these bits is a 1. The complexity of this problem is that it's NP complete. And it is fixed parameter tractable using the color coding algorithm. There is also the approximate counting problem, where we want to count the number of paths, but we want to count them up to a factor of 2. Then, instead of 140, we might be content with 128 as the answer, because that's up to a factor of 2 equal. What this means is that we want to know the position of the most significant bit in the bit representation of the exact number of paths. This problem is again NP-hard, since it generalizes the decision problem. And it's also FPT, which also follows from the color coding algorithm. Finally, and that's the problem that we study in our paper, there is the parity problem. How many paths are there? Modulo 2. Here, in the bit representation, we would just look at the least significant bit. The complexity of this problem is as follows. The problem is parity P complete. That's because the problem generalizes Hamiltonian path. What was open prior to our work is the parameterized complexity. We find out that this problem is parity W1 complete. So it's unlikely that there is an FPT algorithm for this problem. Here we sketch the hardness proof for the parity problem. The proof is via parsimonious FPT reductions. So we start from counting k-cliques modulo 2. This problem is more or less by definition parity W1 complete, because it defines or can be used to define the parity W1 problem. From this problem, we can reduce using known reductions to counting colorful H subgraphs in graphs G modulo 2. And our contribution is a reduction from this problem to counting ST paths in directed graphs G prime modulo 2. From there, we have a simple reduction back to counting K paths in undirected graphs modulo 2. So if we have these three reductions, then we establish that counting K paths in undirected graphs modulo 2 is parity W1 hard. Here's the main reduction. At the top, we have an instance of the colorful H subgraph counting problem. So we are given a graph H and a graph G, and we want to count H copies in G that use all of the colors. And the colors correspond to vertices of H. In our reduction, we transform the graph G into a graph G prime, which is basically following a Eulerian tour through the different color classes. And we have canonical paths, so-called canonical paths, start at S, follow each layer here, so they basically follow the Eulerian tour, and end in T. These canonical paths are supposed to correspond in a one-to-one fashion to H subgraphs in G. So when we count these paths, we will also encounter some bad paths. Paths that don't follow this canonical structure. But we can show and construct this graph in such a way that bad paths cancel. So whenever there is a bad path, there is some other partner. They pair up and cancel. Finally, we come to the third section, which is about matching-splittable graphs. This is our positive result. Finally, an algorithm. The theorem is that if H has a matching split number of S, then this problem can be computed fast. This problem is to count H subgraphs in G modulo 2 to the T. And the running time of this algorithm is n to the order T times 4 to the S. So in particular, This algorithm is polynomial time if S and T are constant. But what is the matching split number? Here is an example graph with matching split number at most 4. If you look at these 4 vertices and remove them, then what remains is the top of the graph, which is a graph of degree at most 1. So it just consists of isolated vertices and isolated edges. In general, a graph H has matching split number S if we can remove S vertices from H to get only isolated vertices and edges. The algorithm for this problem is supposed to count graphs H of bounded matching split number in a large graph G. So every copy of H in G is supposed to be counted, and then this number is to be taken modulo 2 to the t. In order to do so, we guess the location of these S split vertices using exhaustive search. This only takes time n to the s, and we get the images of these split vertices in the graph G, and we can check that the edges that we need between these vertices are actually present. And then we color the rest of the graph using these 4 colors. And we color every vertex, for example here with yellow, if these vertices are neighbors of the yellow vertex. And the yellow vertex is the image of the vertex of this split vertex from H. So we color in yellow every neighbor of the yellow vertex. And in this way, we color all vertices of the graph G with possibly multiple colors, depending on their neighbors in these split vertices. Then we remove these 4, in this case, split vertices, and in the rest of the graph, we count colored matchings. So this is a colored matching. At every vertex, we have 1 or multiple colors. It could also be no color at all. And this color indicates that in the graph H, we had that particular vertex as a neighbor. For example, these 2 vertices had the green vertex as a neighbor. This vertex had green, yellow, and red as a neighbor, and so on. So we compressed this graph H a little bit into this graph, which is now just a colored matching, which is just a graph that consists of edges and vertices. And we want to count colored matchings in this graph. So each color here is a demand. We're only allowed to move this vertex, for example, to the green area here, and this vertex to the intersection of the green, yellow, and red area. So this edge could move here. This vertex was supposed to go to the yellow area, so it goes here. The remaining vertices might be arranged like this. So to repeat, the structure of this algorithm is to guess the location of the S split vertices, which can be done using exhaustive search because there are not too many of them, just a constant number. And then what remains is the problem of counting colored matchings in the graph, which we don't yet know how to do. So how do we count colored matchings? To do so, we use a theorem which is based on Hirai and number 2008. They studied the Hafnian of a matrix. The Hafnian is related to the determinant and the permanent. It is the sum over all perfect matchings, M, in some graph. And then you take the product over all edges, UV, that are contained in the matching. And then you look at the entry AUV of this matrix A and take their product. Hirai and number basically show that this quantity can be computed in time n to the O of tr, where 2 to the t is the modulus that we're looking at. So we're looking at the ring z 2 to the t. We are over the integers modulo 2 to the t. And we actually look at polynomials in R variables. So each entry of A is a polynomial in R variables over this ring. And this theorem shows that we can compute the Hafnian, which itself is a polynomial from this ring, in this time. Our basic idea for counting colored matchings from this point is to, in a way, identify colors with variables and to compute the Hafnian, extract some coefficient, and extract it in such a way that the color demands from the colored matching are satisfied. Let me summarize results on the parameterized complexity of subgraph problems. In this figure, we start in this rectangle here, and we look at the 2 points, grids and bicliques. It has only recently been shown that deciding whether there is a grid or deciding whether there is a biclique is W1 hard. When the tree width of the pattern graph is bounded, then deciding whether the pattern graph exists in the host graph as a subgraph is fixed parameter tractable using color coding, which is a classical, or by now classical, algorithm. If you further restrict from bounded tree width down to bounded matching split number, then it was recently shown, and we build on this paper a lot by Jansen and Marx, that there is a polynomial time algorithm to decide whether the pattern graph exists as a subgraph. We move to the counting problem. It is known that the boundary between easy and hard is the vertex cover number. If it's bounded, the problem is polynomial time. Otherwise, counting the number of H copies is W1 hard. We have proven in this paper that counting the number of K matchings modulo an odd number Q is W1 hard. Counting the number of K-paths is also W1 hard when counting modulo 2 to the t. And finally, we've seen the algorithm, which is a polynomial time algorithm for counting modulo 2 to the t subgraph patterns that have bounded matching split number. This leaves 4 areas open. On the top left, of course, we have the big open problem of determining the W1 hardness of all subgraph problems when the pattern graph H has unbounded tree width. And these 3 areas we conjecture to be W1 hard.